Alright, this is a tutorial on the class action lab. We did this lab earlier in the semester, but just to try to help you out with predicting products and balancing those equations and trying to see what's happening in those labs, I'm going to try to walk you through some of the examples on here. So I'm going to try to give you an example of each one so that then you'll be able to look at the remaining pieces and hopefully you can produce. So we're putting two pieces together. Okay, two or more pieces and you're producing a single product. And so you had a piece of magnesium ribbon, you put it in your tongs, and you put it in the flame where it produced a very, very bright light. So what we need to do is figure out what was on our reactant side. So obviously we have magnesium. We're going to have magnesium on there. But we have to think about what else is on there as well. We can't just have a single product or a single reactant in this case. So we need to figure out what else is going on here. So we're burning it. And so we know that when we burn something, the other thing that we need is oxygen, which is just being pulled from the air, which would make sense why we didn't add anything else. So we're going to have oxygen. So I didn't tell you these things in here, but this is sort of the process of trying to figure out what is going on in your chemical reaction. We know the reactants that are going in there. We knew for sure that there was magnesium, and then logic, prior information tells us that you need oxygen as well. So knowing that this is a synthesis reaction, then we know that we're going to have a single product. So that means that magnesium and oxygen are going to have to be combined together. So where some people struggle is trying to figure out in what proportions. The obvious answer that people want to write is MgO2. So they just think, all right, I'm putting these two things together. However, that is very much incorrect. And the reason for that is if we think back to when we were forming ionic compounds, if we think of magnesium as having a particular sized charge. So looking at the periodic table, we know that magnesium has a 2+ charge. Then we also have to take a look at oxygen. So oxygen has a 2- charge, an equal sized charge to magnesium. So we know that positives and negatives go together. The positive of the magnesium is going to attract to the negative of the oxygen. But what we're going to end up with is we only need one of each because they are the same size charge. So even though a lot of people want to put this 2 on here, that is not the route you want to go. Okay? So there is our first product. Okay? But it is not done. We still have to balance our equation. So we have one magnesium on the reactant side, we have one magnesium on the product side, so that's good to go. We have 2 oxygens on the reactant side and only 1 oxygen on the product side. So we're going to place a 2 in front of our magnesium oxide compound there, which changes our magnesium, so we can come back to this side and balance this. Okay, so now we have 2 magnesiums on both reactant and product sides, and we have 2 oxygens on both the reactant and product sides. Okay. The second part of the synthesis reaction, I'm going to give you a little bit of a hint. We were working with litmus paper, and we determined that the solution, once we put this compound, combined it with distilled water, we ended up having a base. Okay, and so just to try to have you think about that, I'll help you out with this first part. We're going to use our product from step 1, and you were told to, let me jump back here for a second. You were told to place 1 to 2 drops of distilled water. You didn't want too much distilled water because then it would be so diluted that you wouldn't notice that it was a base when you tested it. But we know that we're going to put water on here, so we have H2O. and we're going to get a product. Now, this one I'm not going to tell you the product for, but what I want you to think about is what makes something a base. And we've discussed this before. A base is a hydrogen acceptor. Okay? And one of the major types of hydrogen acceptors is hydroxide. So I just want you to keep this in mind. I helped other students with this, so I want to give you the same opportunity. Hydroxide is the polyatomic ion that is made up of oxygen and hydrogen. It has a -1 charge, so that would make it very easy to bond with a single hydrogen, forming water. But in this case, it's going in the opposite direction. So that magnesium oxide and that water are synthesizing, okay, so they are being pulled together to make a single product. And that's what I'm asking you to do. But a big hint here, this is going to be part of your product. Okay? It has to be part of your product, because if it's not, then you'd have to account for that base somewhere else. And there are other ways to get bases, but this is that hydroxide ion is one of the very, very common ways to get a base. Okay, so moving on to our decomposition reaction. Now, there's only one decomposition reaction here, but I think this will be a great example, because in your lab report, I'm actually not having you write a full lab report on this activity, but I want three things. I want an equation that shows the reactants and the products that you predicted. I want you to balance that equation, which we've already done with part 1 of the synthesis reaction. So we did 2 of the 3 things that I'm asking you to do. And then, when possible, give me some sort of evidence. Tie back what you saw in lab to what you think is going on in the reaction. Tie that back to your products. So looking at part 2, I told you that you're going to be using this hydroxide ion right here in your product, but that's going to help explain something that you observed in the lab. It's going to show you that there was a base there. That would explain why your litmus paper turned blue. So that would be a piece of evidence. But I'm going to jump over to the decomposition reaction. And so what it tells us is that you took copper sulfate pentahydrate. Okay, that is a single item. Okay, it is copper sulfate, copper 2 sulfate. Okay, so this is copper with a +2 charge, bonded with a sulfate polyatomic ion, so CuSO4, and it is bonded to pentahydrate. Okay, so penta, looking at our previous knowledge, penta means 5, so think of the pentagon, 5-sided building. So 5, and then hydrate means water. So we have 5 waters. Okay, so that's where our pentahydrate comes from. Now, this is decomposing, and this is the part that some people struggle with, is they look at this and they think, oh, well, there's really 2 things here. This is all part of the same crystal. This is that bright blue crystal that I gave you in the test tube. And I asked you to heat it up. Okay, and as it heated up, then the crystal went from blue to white. Then we waited a little bit, we waited for it to cool, and it went back from white to blue when we added a few drops of water. So that could tell you that the water was responsible for the color change. So that would be a piece of evidence there. But when you're heating it up and you saw some steam and some condensation at the top of your test tube, where the test tube was a little bit cooler, you saw water collecting up there. So that might have been a good hint for you that this crystal that was originally one big piece has broken apart into the copper sulfate compound, which is the white crystal, and then separate from that is the water. Okay, so I really did that one for you. It broke apart into 2 pieces, so it was a single piece. Now it is in 2 pieces. Okay, that is a definition of decomposition. You're breaking it down into smaller pieces. Okay. So next, these will be a little bit different because the single replacement and double replacement reactions, I have 3 of each. So you will actually be able to do 2 of these completely on your own. I know synthesis, I helped you out a lot on both parts. Decomposition being only one reaction that was going on there, I did that one for you. But for single and double replacement reactions, you should be able to do parts 2 and 3 on your own. So looking at it, we took hydrochloric acid and we put a piece of zinc into it, and then we held a test tube over the top and brought a flaming splint over it, and then you were supposed to just record your observations. So looking at that, what we get is we had hydrochloric acid, that's one of our reactants, and we combined that with zinc metal. So just the end. And this is a single replacement reaction. So our zinc is going to replace our hydrogen. And how do I know that it's going to replace our hydrogen? Because a positive is always going to replace a positive. You can't have 2 negatives, you can't have 2 positives together because they're going to repel. So in this case, what we're going to do is that zinc is going to replace the hydrogen. So now zinc and chlorine are going to be together, and then we're going to have hydrogen by itself. Now, I'm not done here. We have a couple things that we need to talk about, but looking at this, we know that the zinc has replaced the hydrogen. It's now the hydrogen is by itself. But just like up here with the magnesium oxide, people just want to put ZnCl together, but that's not the case because in this situation, we have to look at it in a slightly different way. Zinc, if we look at the back of our periodic table where I have those common ions for you, we can look and see that zinc has a 2+ charge. Okay. Chlorine, looking at its location on the periodic table, everything in the halogens, all the halogens have a -1 charge. So a chlorine is only half as big. I'm just trying to put some visual ideas about how this works on here. Obviously, the charges don't actually have a size, but I'm just trying to put some sort of visual onto the size of the charges. So chlorine is only half as big as the zinc. So with that reasoning, we're going to have another chlorine ion in order to balance out the charge of the zinc. So that means that I need a subscript right over here in order to balance that out. Okay, that's all fine and good. Hydrogen, however, is a little bit of a different story. Hydrogen is diatomic when it's by itself. I gave you a little bit of sort of like a rule to remember. If a compound, or I'm sorry, if an element is by itself and it ends in En or Ne, it is diatomic. And the reason for that is that when you have something that ends in En or Ne, then they, based on where they are on the periodic table, those valence electrons are going to behave in a certain way. So hydrogen has 1 valence electron. It wants to have 2. So what is going to end up happening is another hydrogen, which also has 1 valence electron, is going to be nearby. Now, they can share these 2 valence electrons so that they are both stable. Well, that gives us our H2. The same is true for if I had chlorine by itself, which ends in an Ne. Chlorine has 7 valence electrons. And so it is not stable. It wants to have 8 due to the octet rule. And so when they are in proximity of one another, they can share these 2 electrons, and so they form chlorine gas, which is diatomic. Okay, so just a little bit of memory, bringing in some prior knowledge from earlier in the semester. So keep that in mind as you're writing these things. Okay, and again, looking at some evidence, we would still need to balance this. Okay, so looking at it, we have zinc on the reactant side. We have zinc on the product side. There's 1 of each. I have 2 hydrogens on the product side. but I only have one hydrogen on the reactant side. So I'm going to go ahead and put a 2 there, so that now that my hydrogens are even, hopefully that will help some other things fall in place, which is exactly what happens because I have 2 chlorines on the reactant side and I have 2 chlorines on the product side, meaning that I am all balanced. Okay, looking at evidence, you put that flaming splint up to the mouth of that test tube that was over the top, and it popped. Okay, it burned whatever was in there. So knowing that hydrogen is flammable, that would be a piece of evidence to show that this is the reaction that actually occurred, because hydrogen is flammable. The other option would be that chlorine gas was what was being produced, which is not flammable. In addition to that, it's poisonous, so logic would tell you that I probably wouldn't be exposing you to a poisonous gas. But that's just evidence to show that this is the reaction that is occurring. Okay? One more. The double replacement reaction. So we put 5 milliliters of lead to nitrate, which I warned you about does have some potential neurological effects, especially for women who are pregnant. So lead to nitrate, lead with a +2 charge, and then nitrate has a -1 charge. So I'm going to need 2 of those. And then I am combining that with potassium iodide. So it's a double replacement reaction, meaning that the potassium and the lead are going to switch spots, and the nitrate and the iodine are going to switch spots. Okay, that's what we looked at previously, so now we're just applying it in real scenarios. So if the potassium and the lead are going to switch spots, that means that the potassium and the nitrate are going to be together. Again, a lot of people want to put KNO3 but that would be incorrect because potassium has a +1 charge and nitrate has a -1 charge. So you only need a 1-to-1 ratio for those 2 ions. Okay. Secondly, now our lead is going to be with our iodine, so we end up with PbI2, because we know that lead has a +2 charge because it was lead 2 nitrate, and iodine has a -1 charge, meaning that I need 2 iodines for every 1 lead, just like we did up here with the zinc chloride. Okay, so just following our general ion bonding rules in order to make those, if we can do these types of problems, you should have no problem with the quiz that we'll be taking in the near future. Okay. Again, all I'm looking for is for you to write the correct equation, predicting the appropriate products, balance it, and when available, try to provide evidence. Some of these are a little bit harder than others to provide that evidence for. We talked about solubility and solubility charts, so that would be one way to identify that the PbI2, the lead iodide, is insoluble, and so it does not dissolve in water, which is what gives you that bright yellow precipitate. So it looks like a chunky powder in the bottom of your test tube. So that would help explain what's going on. For most of these, you can provide evidence, but some of them are going to be a little bit more difficult. Again, if you have questions, let me know. Otherwise, I'll expect that you can get this turned into me before we hit the break. And good luck.